Hello boys and girls. So in the next video, next week, I want to do a video on the anti-classical mathematics of Brouwer, and in particular locally constant choice axioms. So anti-classical in the sense that it directly contradicts classical mathematics. And there we will talk a little bit about topology, and it might be a little bit more difficult to follow than what I want to do as a warm-up here. And it's a substantial warm-up. I will certainly talk for an hour or so, where we discuss axioms of the other well-known anti-classical school, namely the Russian young Markov school, because I think it's a little bit easier to wrap your head around it, and certain points that I want to get across about function spaces are true there in just the same way. And so in this video, I will motivate, for example, the formal constructive church thesis that all functions between the naturals are computable. And to get there, I want to do substantial sort of recap on arithmetization that was first formulated in the Gödelian incompleteness theorem. So we will cover this. Probably the first 20 minutes is Gödel. As a side, a few things pop out. For example, the constructive disjunction property. We will talk shortly about the existence property. It's like features of constructive theories. We will talk about halting problems, and then discuss functions and the anti-classical semantics. Okay, so with that said, I might also mention that I have some videos which go very much in this direction. So I have a video from 2 years ago called 4 Freebies of Constructive Arithmetic, and in it at the end I already discuss some of the halting problem, disjunction property relations that also will show up in this video in much more detail, and I have a video in which I basically wanted to list out various things that are possible, especially in constructive set theory, a little bit topos theory, regarding also function spaces and these kind of things. So there is like a full list, which I don't think, apart from some threads on Markov law, are anywhere like collected in this way. This goes very much in the same direction that we will discuss here. And I have various videos in this direction in my logic playlist. So there is a video on computably enumerable sets, which are going to show up in this video as well. This is standard computability theory. And then more motivating in the constructive direction, I have this video on the failure of the Königs lemma, which is one of my favorite videos that I've made on the whole channel. So these are some recommendations that go in the same direction. However, this video might be also a good start into this sort of range of topics. Okay, and with that said, let's jump into the arithmetization part. I wanted to be even a little bit more explicit. I wanted to say constructive, but a little bit more explicit in this video, and I will not do the 50-page textbook introduction to arithmetization, but I will pick out the relevant pieces for our discussion of the anti-classical semantics of mathematics as such. And for this sake, take out the important steps based on a small dummy system, so to speak. We do a Hilbert system where we have just modus ponens as rule of inference, and we have 2 axioms, and you see them here on the screen. These are very standard axioms. So this is the tautological form of implication, introduction, and then some Frege axioms that tells you how to chain things together. If you have not seen them, you can click pause and think for a second if they make sense to you. But they are super standard, and I will use these small systems to give you like examples of arithmetization so that we in the end understand where undecidability kicks in, which makes then anti-classical axioms even possible if you reject excluded middle. So while I discuss these things, it's important that you listen closely and you might even want to write down a few formulas that you see on the screen so that you can refer back to them back when I'm at the later part in the video. You will not need that, but you can, and it is, I think, rather important that you, and this is sort of the point I want to make, that you keep track of which things that are showing up in our discussion are computable, even primitive recursive, and not computable anymore. Because what's really important here to understand how you can consider all functions from end to end to be computable is to have a feeling for when uncomputability, so to speak, kicks in. So basic computability theory stuff, it kicks in already fairly low, but it's like good to have a feel for what works computably and what not. This is sort of the thing that I want to work out here for you. Okay, so back to our system, we have these two axioms for the sake of having a small theory, right? So we actually only have one connective in our whole system here. So we just have the implication, in which terms we formulate our axioms. Phi and psi and later he are going to be like propositional variables. And we have modus ponens. So, if some proposition is true and some other implication is true, where this one proposition we have implies something, then we have collected psi. And we are also going to fix two symbols as propositional symbols. We only have two. We have P. And actually, the dummy proof that I will show you in a second only uses P and implications and correct bracketing. But I will also introduce the bot symbol, bot for the false proposition that we take to represent falsehood, absurdity. And I introduce this just because we will need it for our definition of things that are not computable. Okay, so in our system here is an example proof, right? I don't want to hold myself up too long with this. You can read it here. You have noticed that our theory does not include as an axiom the statement that P implies P, this identity law, true in virtually all logics. And so we need a proof in our system to have it collected, to have like the formal verification that it is among the true statements or the derived statements in our theory. And you have here a proof of it. So we start out with this statement. This is exactly of the shape of one of our axioms. So for your convenience, I have written down the axioms here a second time. We have one propositional symbol P, as I said, and if you plug in the same P for both of these propositional variables, we get this statement. So we know that this statement, we have just derived it. It is true in our theory that P implies P, and we actually want just the later part, P implies P, right? And after some work, we actually arrive at the statement, like the fifth statement in this sequence is the statement. And if we use a valid step along the sequence of propositions, and it's valid if either it is of the syntactic shape of an axiom or if we use modus ponens, then all of the statements in the chain are derived, and we consider the whole chain, in this case of five elements in the sequence, to be a proof of the last statement here. So in this case, this whole thing is a proof of P implies P. We have derived it. If we would stop here, then we have a proof of of this statement. And you can read this and check that every new component here is either of the form of our axiom or we use modus ponens. So for example, here at the end, the fourth statement is of this form. This was the first var phi 1 that we have proven, and we have arrived at this implication, and therefore by one step of modus ponens we arrive here. So this says this is a valid step. Okay, so this is our example proof of a statement that you can keep in mind. And so what makes a sequence of propositions valid proof? Well, all the propositions must be well-formed formulas. In this case, involve brackets and implications. and our propositional variables. And we can always introduce and go to the next component if, as I said a couple of times now, the statements are of the shape of the axioms syntactically, and where these propositional variables alpha beta are themselves well-formed formulas from our vocabulary. And the other option, apart from having axioms, is that we derived the new component by modal exponents. And this means that if we are at position I, then we have a valid derivation using modal exponents if among the other statements that came before it, one of them is this implication, where the assumption in the implication is also part of the sequence, right? So in this case, with I equals 5, this was a valid step from here to here, because this 4 is of this implication form that you need in modal exponents, and the hypothesis here is also part of is also of one of our phi i's, or phi j's is, I think, the notation that comes before I, right? Okay, so this means this is valid. And here already I want to mention, so it's important that we see that to do this kind of checking, that you convince yourself that this is like very mechanical, right? You go through one component of this proof sequence after the other. You have in this case just 2 axioms, right? In the Gödelian, it suffices if it's like enumerable. Like you can also use schemas of axioms, but in this case it's even just finite. You just have to check if it's of the syntactic shape of one of the 2 axioms that we have. We allow ourselves to do enough bracketing so that we can recognize it and recursively like go down into the well-formed formulas and check this kind of thing. So one important aspect of the whole setup here is that this process of checking that the sequence is composed of well-formed formulas and that all steps are valid is this computer implementable or human checkable procedure, right? And now we step this is just some operations that we ourselves do on the propositions, the letters that we have in front of us here, and now comes in the arithmetization, where we keep all these checkability properties, but now we encode things in a sequence of numbers. This is something we do in we recognize in the meta theory that works with these numbers, and we manage in the end to encode all the things that I just said so far in numeric functions. So we have pi, the sequence of all prime numbers, and now is one of many possible injections of sequences of positive natural numbers into a single natural number. I denote this sequence here also with this sort of vector notation. The arrow there just means you have one or more numbers. If you have it in front of you, you can compute the length, right? If you have like a sequence, a tuple, if you have it notationally down, that's clear. And now I define this injection, which takes any sequence of positive numbers and maps it down to another positive number. And I do so by using basically the fundamental theorem of arithmetic. I take each number and map the whole sequence of numbers to this product of primes, where each prime has an exponent 1 plus whatever number I had, right? And so this has the benefit, for example, that if I have a sequence of let's say 20 numbers, right? There's some number, like a sequence might be, I don't know, 9,000, 8,000, 700, whatever, blah, blah, blah. Then if I apply this in this J injection map, then this becomes a product of a bunch of primes raised to the power of this lots plus 1. And so, for example, one thing that I can easily do is check what was the length of the sequence that is given by this number, right? If I pass you some huge number, you can do the prime factorization. By our definition, for each slot, this prime will show up for sure. That's why there's this plus one. And so, for example, if you give you a number and tell you, oh, this comes from a sequence, you can actually check, oh, this comes from a sequence of length 20 because it will have the first 20 primes in it, right? You can do the factorization. You see, oh, this number is the largest prime that shows up in this number that you just gave me. And this is the 20th prime. And therefore, I know that the sequence you plugged in to compute this was the sequence of length 20. Okay, and here I do an example. The embedding of the sequence, which as first element holds the number 9001, and as second element, another embedding of some other sequence, comes out as this kind of thing, right? I start with the lowest prime 2. I do x1 is 9001. I add 1, so I have this factor, and then I have the second component is 3 to something else. And because this is another sequence encoded, this the exponentiation adds up, and you get some gigantic number just from embedding this thing. This is not a very efficient embedding pairing. There's many other pairings that you can do, but the size of them doesn't matter. It is about being able to factorize all these things in principle. So, for example, you can say, oh, I see there's a factor of 3, but it's raised to a power of some number that if I subtract this 1 is again not a prime number, but is something else. So I assume, oh, that must, if it's even a valid image of my injection function, this is another sequence, and I continued with my prime factorization. And in this way, given a number, I can, if it comes from a sequence, reverse engineer the sequence. Okay, and now we also encode our one connective in our theory, right? We had not just we have like two propositional variables, and we have the implication. And I define this function C for code, which to each propositional symbol, in our case P and bot, we will assign some prime number, some larger prime number. And not only for this propositional variable, but also we do it for the implication. We do this by using our embedding and just tagging this thing with a 2. So whenever you find some, in this case, 2 to the power of 3 showing up somewhere, then you knew it came from some implication. Whereas this other well-formed formula you do recursively also like take apart, and once you end up with this hard symbols P or hard symbol bot, you have a well-defined prime number. Here in my example, I say, how about taking 7 and 8, because these are numbers that go beyond our implication encoding. And therefore, you managed to encode recursively not just propositions, but actually this also enables you then to encode whole sequences of propositions, and you can see where this is going. We already had this example with our proof, which was like a sequence of 5 propositions, and now we're also able to just squeeze all of this like recursively into a single number. Everything becomes a single number here. It is worth mentioning that there's like this technical annoying fact that we have an injection, but it's not like a surjection in general, because, for example, if I have the number 10, then with the definitions that we use, this cannot come from any valid sequence, because we said all our sequences have all prime factors up until the length of the sequence, right? So if I have 10, which is 2 times 5, I do not have a factor of 3 in it. So if I give you 10, then you can actually also reverse engineer, or this actually does not come from any sensible object with respect to my coding and with respect to my dummy small Hilbert system here, right? So this can happen. but it's also not a problem. You can always recognize computably that some number fails to be an object with respect to the system. Okay, and here all the things that I emphasized so far, I write down again here. The things that we want to make sure, this is like important part, to make sure all this embedding and factoring, dividing by numbers to see how far we have to go, is all computable, and also like given a number, that its prime factors cannot be bigger than the number, so it's upfront that it will be maybe a large but a finite number of steps to get to this taking apart. And with this at hand, we now define this important predicate, which I here called, this is not standard notation, but it's just for you to be able to follow this if you have not seen this before. I call is proof of, in our system T, if this n, some given natural number, which I just argued, you can decompose and see if it's a sequence and if it's a sequence of propositions, and which I did not emphasize just now, but which is also the case that you can also check that it's a valid proof, that all, this is the axiom or modus ponens thing, that you can check, are this not just propositions that are represented by this sequence, but is also every new element introduced by the use of an axiom or by modus ponens. So is proof of, in our theory T, we want this to be true, we define this to be true if the given number represents a sequence of propositions of well-formed formulas that are actually a valid proof in our system of the proposition that is encoded again with some number. So C of our proposition, our well-formed formula, is also a number, and we have here basically a binary two-array predicate, which is computable, where we have two slots, and in the first slot we plug in some number which can be, for example, recognized as a proof, and the second slot can be recognized as this a proposition, and we can check this. This is just checking, hey, here's my proof. Is here's my proof candidate is number. Is this a valid proof of the other number that I've encoded? Okay. And so, for example, we already know that because I have showed you a proof of this implication, P implies P, right? You know that indeed there exists a number such that this number represents a proof of this proposition. Right? This proposition is I can embed into a fairly small number, relatively small, right? It will be 2 to the power 3 times 3 to the power of, and then I go to the prime that is P. I think it was 7. So C of P implies P is some number, and I showed you the proof. This will be a gigantic number because it's like a sequence with 5 elements, and the elements themselves had a lot of implications, blah, blah, blah. But because we can go back and forth between the numbers and the proof that you have seen on screen, you know that there is a number representing a proof in our system of this kind of thing. Okay, so this is how this is proof of thing works. And now, this is just a side note. We do not talk deeply about the proof of the incompleteness theorem in this video itself, but I will take for granted that you know that the consistency of a system in a strong system, if it's consistent itself, and we can also make some soundness assumption if you want, is not provable in the systems, yada yada. But I want to just mention, because we have already now developed all this kind of notation, how this goes further in the actual proof of the incompleteness theorem. So there is some technical results that were achieved there by Gödel. I just will quickly go there. So this is the beta function, which helps you, not just encode sequences and numbers, but also encode quantifiers in a predicate logic. I just have my Hilbert system with propositional variables, but you have to extend this if you actually want to capture piano arithmetic or whatever. So this is some number theoretical results that he used to get some nice, essentially, number theoretical results. And then, of course, he has his diagonal result, which he proves in generality and then applies to the situation at hand to derive the statement that I will write down for you here just now. So what he ends up with is that, he finds there is like a proposition in your theory such that the theory proves that this proposition is equivalent to this ugly statement. And I just mention it because we have now the whole notation to write down. So it says that G is equivalent to this implication, which is internalized in the arithmetic, in this case T. This T is not a Hilbert system in Gödel's proof. Obviously, it's like a system which can do arithmetic such that you have all the symbols that you want to talk about. But you have then the statement that the existence of a proof for G, right? This is just the same situation we had here, but with this particular G that he shows you can construct, is implying this statement, which says there is a proof of falsehood. Which you really do not want your theory to prove this. If this statement holds true, and is sound with respect to your proof calculus, then you're in trouble, because then you can have falsehood proven, and then by the axiom of explosion, if you have it, everything just follows. So this is a very proof theoretic version, I put it in quotes here, of this statement, right? So this basically says G is provable, right? Here's true. I do not go into provable true discussion here, but you see the analogy here. So you have here this G. This is actually stronger than just saying this claim is stronger than just saying G is true, but it actually tells you there is a proof. It claims there is a proof, and this represents in the same way falsehood. And so this thing is a sort of negation of G, right? You can see this. G implies falsehood with a bunch of proof theoretic wrapping, and the whole statement says that this is equivalent to G. So this is a version of G implies not G in both directions. Okay, so this is just as a side note. From this, then you can conclude meta-theoretically that the consistency is not provable because you have this issue. Okay, and then there's another side note that I want to make here that will become relevant later again. So if I have some proposition, I call it Q here, right? And I know that this statement holds. So there's this claim: there exists a number such that this number represents a proof that proves, that proves Q in this sense. Then, of course, you know that the system T entails Q, right? I think this should be clear. Yeah, and so if you actually have this, here I want to emphasize the difference between having a number in the meta theory, like having a number in the meta theory, like hard, so to speak, is like having a term. For example, in piano arithmetic, you have the symbol 0, which per the axioms represents a number in your theory. Then you have this injection S, which maps every number to another one. And this symbol S0 represents a term. So this is sort of a hard number. Having a hard number in the meta theory is a priori stronger than just having like a statement which says there exists some number with some property, right? So the big point here is that just if you have like this symbolic representation of existence, then this is like a priori different from having actually like a term in terms of the symbols of your theory, right? The existence statement is much looser. And the thing is, if you have a theory with the existence properties, then these actually always go together. Then you have you can prove of some frameworks the meta theoretical property that if you have derived that a certain number with a property holds, then this implies actually that you actually actually have like a term in this sense. This is like a meta-theoretical result. We are playing with different levels here, but the point is that this is usually, like in general, not given at all, and we will actually see a counterexample in any classical theory with a comprehension axiom. So in particular, some classical set theory, which violently violates this. So some theories have this sort of property, which is nice, and these are constructive theories almost by definition. And some violate it, and we will see how this fails in the language of the of arithmetic with the least number principle. And similarly with set and induction, set induction in set theories. Okay, so I changed the language a little bit. The fact that we can, as I argued, computably check this is proof of predicate. I want to explicitly use the notation of functions now and recast this statement in terms of functions, because our anti-classical computable semantics are really very much about functions later. So I take this statement that you have already seen now in the side comment on this Gödel incompleteness theorem, right, is proof of the number of absurdity. And I just give it the name, I call it here just isbot for brevity. So the number n represents a proof of the falsehood encoded in this sort of way. And I define this function. This is basically the characteristic function on the naturals, where the characteristic function says 1, it says yes, if the natural corresponds to a proof of falsehood, right? Yeah, and of course, when you talk about arithmetization, you might not even have a primitive bot symbol. In classical logic, you generally use the negation. Constructively, you can introduce the negation by this implication. It's just a side note. And in the same way, when people discuss the Gödel proof itself, then a bot, instead of this, you actually take 0 is 1 or something like that. And I use this notation injection and C and so on and so forth. For this coding, there's like various like symbols. I'm fairly brief in this video about like the symbols. I didn't want to introduce even more notation, and for this purpose I've also chosen this very small theory. But just for you, if you want to recognize this, a lot of the notation I used above is not completely standard. In particular, when it comes to this is proof of and code, I was just more explicit in this video, so you can follow the notation on screen. Okay, so I emphasize again, this characteristic function that checks whether a number is a proof of absurdity is always with respect to a particular theory, right? Because for us to check, is this a valid proof, means valid with respect to the introduction of elements in the sequence, which means I only use these two axioms, for example, in our dummy system. So this is very explicitly, hey, what axioms have you actually chosen? And this is, in this way, it comes in that you talk about a particular theory, among other things. And here, when I talk theory now, and I talk about, if I make use from now on about the incompleteness result, then we want a theory where all of this stuff that I just discussed is actually internalizable in the theory. So we want a theory of arithmetic, in other words, or that has a model of piano arithmetic in it. Okay, and so now with this falsehood proof detector function, he of bot, if all numbers are not a proof of falsehood, then this, as is reasonable, is like an expression, is like one possible expression of the consistency of our theory, right? A theory, for it to be consistent can formally be defined as it's not possible to prove A, like for any proposition A and not A both. It is like you can find two proofs of A and not A. And because of the explosion, if you prove absurdity, then you can prove everything, and in particular it's inconsistent. If a theory is inconsistent, then you can use A, and A implies absurdity by modus ponens to improve bot. So these are equivalent ways of talking about like having an inconsistency. Finding any proof of inconsistency means your system is inconsistent. If you find any proof of inconsistency, then there's also many other proofs, because you can always make a proof longer by doing, unnecessary extra steps and so on and so forth. So if there is one proof of inconsistency, if there's one proof of bot, you have an inconsistent system. What we actually here write down is the system is consistent if no proof is one of falsehood. And for talking this constructively, it's actually a little bit even better to introduce the inconsistency statement. It's also not necessarily a standard notation, but it's not complicated. So, you have this this statement: there exists a number such that our characteristic function returns the value 1. Then you have this problem. So this is an expression of inconsistency. I write also the formula for the level in the arithmetic hierarchy, so that you can keep track of the quantifiers, which is important. So this characteristic function is a recursive function, right? You can write it down with recursion or while loops. And this is as good as having a number, because you can always compute what the value is with a function per definition. The Gödel basically introduced all this recursion shenanigans to do his proofs. And so this is a statement of sigma 1 classification, because there's exactly one quantifier, no other quantifiers here. If you negate the inconsistency, right, and you have negation of existence, this is equivalent, even in constructive logic, to the claim that all elements give a negated proposition. I want to emphasize also that the other version, where you say exists not, implies not for all, but not in the other way around. So this is the one equivalence that also holds constructively. This is the one we need here. We can also see, therefore, that the negation of the inconsistency claim is actually equivalent to the consistency claim, right? The negation of the inconsistency claim is equivalent to the consistency claim, because if you know, by definition, the function has domain 0 and 1, then if it's not 1, then it's 0. If it's not 0, then it's 1 for this function, because everything is computable. This is no problem of switching around in there. Okay. I know I'm a little bit maybe overly explicit about these kind of things, but maybe if you don't have it like in petto, and you don't have like as strong as a feeling, you get the feeling, like you get the understanding for which things are computable, which not, which manipulations can you do legally in various theories and systems. You get this very quickly, but just for viewers to maybe have less confusion than in some short text or Wikipedia article, I'm a little bit more of a boost here. I also want to mention as a side note that there's like a nice, maybe surprising theorem that says this characteristic function, you can also encode this with polynomials. You can find a polynomial in basically any arithmetic theory, and in sensible arithmetic theory, where the inconsistency is found exactly when this polynomial in the integers happens to have a 0 somewhere. It's just a side note, but you can think of this recursive function also like as this polynomial. And so you see, it's actually, this is a particularly strong statement about how easy it is to compute it, because of course evaluation of polynomials is just arithmetic operations till you arrive at the standard term. Okay, yes, and of course now if you have a consistent theory, and for simplicity, like I assume also the theories are sound. I will not go into detail about all the levels of soundness and what shenanigans you can do with this, but if you say that if our theory is like a good theory, it's consistent and sound, then of course, for sure, it does not prove an inconsistency. It does not claim that there exists numbers which represents proofs of falsehood. And then, of course, the famous Gödel result exactly says that the theory can also, by his diagonal result, not prove its own consistency, or in our language, it does not prove the negation of an inconsistency. Okay, so we have this. Okay, we have now argued in fairly detail that most theories, like at least the strong theories that are consistent and sound, do neither prove an inconsistency and the consistency of this theory, right? And consistency is here meant in this arithmetized, encoded proof system encoded fashion. And so this means we have two statements which are neither of them are provable. They are also like the one is a negation of the other. Okay, I had to cut the video because I did a copy-paste error where I copied this S by Gödel and the not V dash accidentally, but now I have corrected it. The script here is fixed again. So now we proceed by recognizing that our classical theory, right? In a classical theory, per the law of excluded middle, which in this video I call PEM, principle of excluded middle, for any statement, either it or its negation holds as a statement using the disjunction, the or in the language of our theory. This joint statement, P or not P, holds automatically by axiom for any statement P, right? So in particular, the theory proves our proof is inconsistent or not inconsistent, as well as it proves it's consistent or not consistent, right? For any proposition P, it proves these kind of things. And now this is, however, an interesting situation, right? We have a statement P, for example, the consistency statement, such that it and its negation are not provable, but the theory still claims that either of these things hold, right? You can say, like, under the assumption that, like in a metaphorical understanding of the like a Platonic realm, things are true in this Platonic realm or the model or not, and so you can argue for adopting the law of excluded middle easily, and this is like done. But if you couple like truth and provability more, then this is at least odd, right? And what a constructive theory does, basically by construction, you basically call the theory constructive if these sort of discrepancies between individuals and the joint claims with the disjunction do not happen. These are this disjunction and also existence property, which we talked about before, with the existence claim and the actual existence of a term. A constructive theory is nice in that it is basically characterized by properties like such that if a theory proves the disjunction of two statements A and B, then it's also the case, and this is like a metalogical if with double F, like a by implication, metallogically, if it proves this disjunction, then actually at least one of these two is also the case, right? Of course, for every trivial A, like, if I say 2 plus 3 is 5, this is a true statement, then disjunction also holds by disjunction introduction, right? If 2 plus 3 is 5 is provable, then it's also provable that 2 plus 3 is 5, or the axiom of choice holds, or 10 plus 10 is 20. So this direction is clear. The other direction, as we saw here with the classical theory, is completely violated in the classical case, right? So Zermelo-Fraenkel choice proves that the continuum hypothesis is either true or false in this sense. Like it proves, CH or not CH, but it proves neither of these things. Whereas if you say, hey, I'm dealing with a constructive theory, and I say it this theory proves the excluded middle statement for some proposition P, then if you know that the theory respects the disjunction property, then also one of those is still provable, right? So this is the disjunction property, and just by knowing that the theory has the disjunction property, you can basically derive a lot of new, like more independent statements. Like for example, the double negation of an excluded middle statement, like not P or not P, is always provable in certain constructive theories like Halting arithmetic and so on. And so if the theory is consistent, then the negation of the excluded middle statement is not provable. And so if we have an excluded middle statement which is not provable, then the excluded middle statement is also not provable. So describing this is a little bit annoying. I do this here on the fly. But you can use this obviously to generate new statements which are not provable or independent. And in particular, we will use this knowledge of the failure to prove certain instances to make room for the anti-classical semantics, right? Now that there are certain statements which are not provable, our theory is weaker. For example, Halting arithmetic, HA is weaker than PA in this sense that there are certain statements that it does not like straight out prove, and therefore we can also run into less contradictions. By being weaker, we have suddenly more room for other axioms. Okay. So one thing that I also discuss here, because it just offers itself up as a side note, is the least number principle, right? So if you postulate induction, you can prove strong induction. This is like a statement with similar to induction. Induction is formulated with like successor. Strong induction is formulated with the order symbol, which you can introduce as in any semi-ring, whatever. You get this least number principle, which says if you have any proposition Q, if the proposition Q is validated by any number, then so piano arithmetic gives you, then there exists a number which also validates Q, and such that there is no smaller number that validates Q, right? So read this for a second, think about it. It says if you interpret Q as a set, right, a sub-collection of numbers, of natural numbers, that is not empty, that is inhabited by at least some number, then in this sub-collection there's also a least number, a smallest number, which has this, right? I mean, this is very intuitive, but which turns out a very classical statement for a general notion of predicates and subsets. So it sounds like normal, but constructively you easily run into problems, as you will see in here in the following statement. So for Q of n, take this simple statement, n, relatively simple statement, n can either be 1, then Q is true, or it can be 0 and this proposition here holds, then n is also in it. And if you take a bigger number, then it will be false. So Q of 7 will be false because we know Q of 7 is neither 1 nor 0. Like 7 is neither 1 nor 0. So these are out. The number 1 is totally in, but the number 0, it's a little bit fishy. It depends on this independent statement, right? So the thing is, if you claim there is a least element for this set, right? So the set holds nothing bigger than 1, it holds 1, and whether it holds 0 is contingent on the consistency of the theory, then the theory cannot, for example, it cannot prove Q of 0, right? If our theory will prove that the least element for this Q is 0, then this would imply that the consistency statement is also true, and so we know that if our theory is consistent, if we judge this thing to be true, right? If the consistency statement is true, then this set that we are talking about is just a set which contains 0 and 1. But because of our construction, because of this like silly Q statement here, we have constructed it in a way that the theory cannot possibly prove that 0 is the least element which validates Q, right? I mean, think about this a little bit. Read what I've written down here on the screen. And convince yourself basically that the mere existence claim of a least number is basically equivalent to the excluded middle statement for consistency here. And so in this way, a constructive theory cannot prove the least number principle, because a constructive theory which has the existence property, if it were prove that there is a least element for this set, right, for this set, then because the theory has the existence property, it should also be able to give you a term. It would give you the symbol 0, or it would give you the symbol S0, which is the first number 1. But the theory, like by Gödel's incompleteness theorem, cannot entail that Q of 0 is the least number. It can also not entail that. It can also not entail that 1 is the least number of this set, because then there would be the implication that the consistency is false. Okay, so I am not sure how solid my explanation just now was, but you might be, if you write down these sets and think about it a little bit, it should be clear that the system, the theory with the existence property should not make the claim that there exists a least number, because then you would be able to have this least number. Okay, but then here, as a side note, also the double negation again works, right? The Halting arithmetic can prove that it's not possible to rule out that there is a least number. If it would be possible to rule out that there is a least number, then Halting arithmetic would not be compatible with Peano arithmetic, right? You can add any classical axioms on Halting arithmetic in the same way that you can add for some nice type theories. You can have a constructive type theory, but then add classical axioms on top of it. As long as you have a vanilla constructive theory which has no anti-classical axioms, then you should be able to add classical things on top of it. And so it cannot be that this constructive theory invalidates, like actively negates any classical statements. Okay, and now we move over to the Halting problem. So I hope you followed all the Gödel stuff, because now this language introduces even more parameters. It generalizes certain things, like this non-computability results. They get even worse with sets which are not computably enumerable. Okay, and I will motivate this now. So we have this Kleene predicate, which is also a predicate which is constructed. You can think of it a little bit like this is proof of predicate that I introduced previously, right? You have this T, and it has actually 3 number inputs. I remind you, our is proof of predicate had 1 number input n, and it was about, does this n represent a sequence of propositions, and if yes, is it a valid proof in our system? Now we still have the n, but we have 2 more arguments, and we think of them as E being the code in our enumeration of computer programs, right? So for example, you can think of Python, and a valid Python program is just basically a string, right? It's like a finite number of characters from a finite alphabet, like ASCII characters, Unicode characters, in a finite file. And so you can also think of it as numbers, right? I mean, every ASCII character is represented by some number between, I don't know, smaller than 300. And so all of the file, we already saw that we can code sequences. All of the file is also just a number. So we can enumerate functions or program functions in this sense. And we have we think of program functions that take integers as input and return I don't know, other natural numbers. And these inputs we call x here, right? And here, this is don't take it too literally, but there's a connection where this sort of framework supersedes the Gödelian framework. It was done a few years later, and you can think of as our proof checking system, where we say, hey, is this number representing a proposition? Is it a valid proof of something? This proof checking system, which we have tuned to our theory phi, is just now one possible function, e, and you can think of x as previously we were interested in the probability of the falsehood, and this is like one input now. So you can think of x a little bit like the code of bot, and e as our proof system. But now we have abstracted this away. We just do computability theory now. We're just interested in all functions and so on. So this is the generalization there. And now we can define this h, which are tuples of natural numbers, right? So we all functions and all inputs such that there exists a t, and I didn't explain what the n here represents. So previously it was about whether n represents a proof that is valid of something in our system. Now we read n as, roughly speaking, for the purpose of this video, as the output of the function ran on this input. Really, n represents something more, like also a sequence is basically like the computational track, the history of the computation. So, if you actually execute a Python program, then it will do what the function body says. Maybe it's an arithmetic function, your Python program, and there's some additions, and maybe at every step you log out what is happening. Oh, now I'm adding two numbers, now I'm multiplying, now I reach into this memory, blah blah blah. So there's a history that documents everything that happens in the function, and you can think of it, this is all like this is all like so, but you can think of it as a history of what's happening up until, and you get n upon termination of e on x, and also this n, also from it you can in general extract what the result is. This is all details, and this is like computability theory, like straight up computability theory, where these things are introduced properly. But for the purpose of this video, think of this statement: there exists n such that t, e, x, n, as there is a return value such that when you run the function e on the input x, then it actually returns with set return value. Right, so this is a halting statement, and this set basically has all the tuples of functions encoded by their computer code and all inputs to these functions. This h exactly holds all these values where e runs and halts on x. Okay, and so the thing is that by these Turing results, this is only computably enumerable. So if you have a program, a Python program, and then an integer input, 9,000, and you run it, if it holds and you wait long enough, then eventually you will actually get the result and it holds. If it does not hold, then you might be waiting because the function has some complicated for loops, and you might be in the bad situation that you actually never find out if it will hold, right? This is like standard stuff. So this is computably enumerable. You can get all functions and inputs that eventually hold with respect to your programming language, but you cannot rule out the other side. And therefore, if you look at the complement, all the tuples which do not hold, then this is not even computably enumerable, because this is basically all the this set is asking for all the situations where you actually run into a while loop, and this is not decidable as per Turing. So, and this is exactly the statement here. Similar to my he of bot, right? there is no function which is a characteristic function on halting on its own input. So here we even abstract away x. We say we run our programs on their own index, and this is this Turing construction. And there's a statement that this is not actually a program in itself, because you get into a contradiction if you assume this exists. Okay, and so for very similar reasons previously argued with the disjunction property and the fact that the statement is independent. For similar reasons, you get that a constructive theory like Halting arithmetic does not prove that all functions hold or do not hold on their own inputs, right? And so here it's important to see this connection with computability and totality. We talk here about programs and functions that actually hold. And in the constructive theory, where we do not have these, we do not get this disjunction for free, right? If we get a disjunction, it actually means something. It actually means we get one of these sides. In the constructive theory, these propositions that are not provable reflect, in a sense, the fact that this to-be function is not actually a programmable function, right? So there is like a close connection between things that are like provable, like for all inputs you can decide in either direction. Like there's a close connection between what you express in your predicate logic formulas in your arithmetic and how programs behave and what can be said about them. And indeed, this connection is basically a perfect match in the sense that you are allowed actually to interpret provability of the constructive theory in this computable sense. And this is what gives room, and you have to breathe over this a little bit. This is what gives room for, and this is like a meta-theoretical result, that there's computable semantics for this arithmetics. This gives room for the possibility that you can postulate that all predicates, right? We're dealing with predicates here, for example, for these kind of things. There's room for the possibility of postulating that all predicates that represent total relations are embodied by a computable function in your program. And this is basically what I just said, is basically the constructive Turing, the constructive church thesis, which later I will actually write down in more formal terms. But here, basically, you can already see it, right? So you can stare at the screen now and see that the non-existence of a program, a function in the sense of programs that does a certain job, is reflected directly in the ability of the system to prove something. Okay, and I want to emphasize that here we have this for all natural numbers E. This excluded middle statement is not doesn't hold that there's a quantifier. Whereas previously we had the situation that we just talked about a single proposition, right? This was like one proposition. This was our E was something like the proof checker, and this is in a sense a weaker statement. This was literally about one excluded middle instance, whereas here we have this sort of uniform excluded middle. So here we have for all, and while by the arguments that I said before about Halting arithmetic being still consistent with Peano arithmetic, while it is not possible to negate an excluded middle disjunction, right? I cannot postulate in Halting arithmetic that the excluded middle statement directly fails, because it proves the double negation of the excluded middle statement. Because there's a quantifier here, I can actually actively negate this statement. So I can add a postulate that says my extended theory, which is stronger than Halting arithmetic, actually proves that it's false that all indices either hold or do not hold, right? We can take this fact that Turing found out that there's there's some codes which do not represent total functions, halting functions, and we can take this result and embody it as an axiom in our theory, and then we get a theory which rejects this claim. This is not an inconsistent theory because it does not conflict with any excluded middle statement, because there's this quantifier in the middle, and you cannot constructively swap it, right? To say it's not the case that for all blah 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 is not the same constructively as saying there exists a number where it fails, and therefore we can live with this rejection of a classical proposition without actually running it into an inconsistency. Okay, so this is all very vague talk. I'm sorry that I didn't write a whole article making all of this formal, but I hope I convey the possibility that this gives here and why it's important that there's this quantifier, why it enables us to make statements which are anti-classical without breaking base logic, basically, right? We do not negate an excluded middle statement, but basically we negate this uniform version. Okay. But there's also this language of we reject certain classical principles. So that you have to watch out with the language a little bit, right? If I say rejected, I usually mean if I would also adopt classical principles, then we would have a contradiction. And so we make our new anti-classical theory. Our theory, we make it anti-classical, meaning it is not consistent anymore with the classical principles, but it does not prove statements which are straight out wrong. It's still a theory that works as a theory, right? It's not a theory that proves a contradiction. Okay, and here is a side note it's actually more than a side note on characteristic functions. I talked this sort of spiel I discussed previously in this video on the 4 freebies of constructive arithmetic. And now that we discussed a little bit how where I suggested that it's possible to postulate that all predicates that are maybe I should have switched the order of the sections, but what we will get to is we will talk about predicates again, total predicates, and we will talk about the axiom that postulates that these are all corresponding to total functions. And what happens then is that in these constructible worlds and constructive worlds, like for example, also constructive arithmetics, higher order arithmetics, and set theories, we can adopt these anti-classical axioms which make statements about functions that are consistent, not consistent, not compatible with the classical world. But what happens there is that we look at certain objects which classically are functions, and we just add an axiom which rejects the idea that they are even functions, right? So what I want to motivate here is that we will now in some detail look at these classical functions, right? Functions conceived in a classical setting, and we want to step out and follow the logical steps that in the classical theory actually turn them into what we call a function, right? Okay, let's just jump into this discussion. So in a set theory, or also second order arithmetic, you have some comprehension. So if I have a predicate Q, and I can write down here, for example, hey, I'm interested in the tuple where the first component x is from the naturals and the second component y is from this binary set. And then if I have a predicate Q, I can write down this object, right? So an element, like if for example x is 7 and Q of 7 is provable, then the then the tuple 7, 1 will be in this element. So this is what we also call a function graph, right? This is like how in the end functions are going to be encoded in set theory. And what I want to like emphasize is now whether this object is a function, meaning whether for all elements x there exists a unique y, will depend on what your theory can prove about these q's. And since you can already see it, here we have q positively, here we have q negatively. Having or not having excluded middle will make a difference with respect to finding out if this graph object is actually a total function. Excluded middle is necessary to actually come to the conclusion that for every x, this kind of thing gives a unique output. Okay, so I step through this fairly quickly now. So I hope it's evident, so that q of x exactly holds when when this clicks, when this is true, when the element x1 is in the graph, and similarly with this negation. So classically we would say that this GQ is a characteristic function for exactly this predicate, right? And oh god, I have so many typos here. This should be there should be no, that's actually this works out. Sorry. Thankfully this is not a typo. So by consistency, both cannot be true at the same time, right? If both are true, then that would imply that both q and not q are true at the same time. So by consistency, we know that it cannot be like this graph object cannot map one value to two outputs at the same time. But only if we have excluded middle do we actually find that there exists a unique return value, right? So we have this equivalence with q and this thing being in it, not q and not q being in it. But we have already seen that there's like statements which are independent, where neither the statements nor the negations I'm running out of voice can be proven, right? And so if q of x, similar to this consistency statement previously, is like independent, and we have a theory with the disjunction property so that we cannot even prove this conjunction, then we can also not get to this existence statement. So long story short, this object, this graph object, if we are in a weaker theory that does not have law of excluded middle, then this does not actually represent the function. It's not like we can take any x and find that there is a unique y, 0 or 1, such that this object holds it. So this GQ is a set in our constructive set theory, but it's not a function, right? So think through this, like maybe pause and think about this. We can use the axioms of set theory, the comprehension axioms, so take a predicate and write down the subset of this thing. But whether or not this is a function in the sense of for every input there exists a unique output y depends on how strong our logic is, whether or not we can actually prove excluded middle for this kind of thing. In a classical theory where q or not q is always true, every graph written down in this way is automatically a function. So there's lots of functions, but in a constructive theory, there are some objects which are just do not turn out to be functions. And so if I write down, for example, the function space n to n, right? N and then set notation n to the n, then if you come from a classical world, you might mistake. And I made this video. I made exactly this point in at the end of this video as well. If you come from a classical world, then you overestimate how many things are actually functions, right? You think certain objects like this are members of the space, like the binary set to the power of n. This object which we call function space. You think that this particular object is a member of this space, whereas in reality what you've written down is merely a subset of this product. So you need strong axioms, these non-classical axioms, to make all of these strange subsets which you've written down in this fashion into functions. And therefore, if you are in a constructive world, it is possible and consistent to just postulate that certain objects which have these undecidability problems are simply not functions, and therefore the function space is just sparser. And this is basically the point that I wanted to do with this whole video. We will get to Brouwerian anticlassical semantics in the next video, where, for example, there's a result that it says all functions from R to R are continuous. And one good way, I'm not saying it's the only way, but one good way to read it is just that a lot of the objects which the classical person thinks, of course, are functions, just do not validate all the necessities that in this theory actually make it a function. So they are just lacking from the function space R to R, right? You can postulate all functions are continuous because the other things that you think are discontinuous functions are not even functions in this framework. Okay, I hope you made this point. So to get to the title of this video, right, we talk about church thesis. This, I should have put this section a little bit earlier because I've already talked about it now, but there is many non-classical axioms. There are many non-classical axioms. One of the formulations is this. This says, if you have any predicate, which is a binary relation like this, right? So it is also total in the sense that for all input there's an output, not necessarily unique in this formulation, but for all input there's an output. So this is like some relation, like I've written down a relation here. Then this axiom CT says there is then a code of a program. So there is a program such that for every input there is an output that actually fulfills it. So this is basically a subset of this relation. If you think of the relation like this, right, here I have a relation with 4 elements. The axiom says there is then a program which is functional, meaning for every input is only one output, right? So in this case, I've written down a function which for x3, x6 and x7 in this case, returns certain values. And in this case, if you look at the numbers, I have dropped this element because, this would be, this thing is a relation. It happens to have one input, namely the input 6 has 2 outputs. A function does not have this. But there's a subset of R which represents a function. This is this object. And the axiom says for every relation, there is not only a function, not like in the axiom of choice way. There's not just a function, but there's actually a code in like there's a program function, a programmable function. This is like embodied by it's saying, this program ran on. Exactly. This program running on X has a execution history, and then this U symbol means that basically the last element of this history is the output. This is similar to the last element of a proof is the statement we want to prove. And so this is a sort of choice axiom. It says every relation actually translates to a computable function. And this is anti-classical because, of course, in the classical world, you can write down relations which do not correspond to computable functions, right? And so this is like one of these axioms, which is a fairly strong existence statement. Is not compatible with the classical world because it basically claims all relations translate to functions. And the fact that this is not classical manifests in the way that it actually, for example, I do not do this here, but it actually rejects this sort of excluded middle statement. This is exactly the statement that I've written down before. So Halting arithmetic plus this axiom negates the for all statement for this disjunction. Again, this is then not compatible anymore with postulating the law of excluded middle, because if you postulate the law of excluded middle, then this statement here is true in there, and the therefore you get a contradiction, right? You state for all true is true, and then there's like literally like you prove an absurdity. So once you have this result, you cannot postulate the axiom of excluded middle anymore. But this statement in itself, this sort of statement with the quantifier, also does not in itself disprove excluded middle. It does not give you a proposition such that the negation of the excluded middle statement is proven false, right? It just blocks excluded middle from becoming an axiom. But because in the constructive logic you cannot pull the quantifier in, this thing here is not equivalent to the statement that there exists an E such that the excluded middle disjunction is negated. You cannot pull this negation through the quantifier. And so you get a consistent system. This is a very nice consistent system which very much reflects computable semantics. It says all relations are computable. And in this way, you have like this world where all relations translate actually to computable functions. And so any other relation is basically not even a function anymore. And finally, I've pretty much made this point now. So I hope this motivates that you can have this system which is not compatible with the classical world, and in a certain sense has stripped out a bunch of objects from even existing as functions. And this particular aggressive axiom, the CT, which makes all functions into computable functions, just even negates that there's any function that is not a computable function. It basically says you're not even allowed to consider certain objects functions. And I also want to emphasize all of this, what we do here, you can reason about it. You can say, okay, there's a function space and it only contains continuous functions, or it only contains computable functions. It's an alternative axiom. You can envision the subset of the normal classical function space, which only has these restricted objects. And in this way, of course, all these axioms can be modeled in set theory still, right? You can say, I model with my classical world a set which just lacks a bunch of objects. And in this way, because you have the set theoretical semantics, all of this might not even be as radical, right? You can just think about it as a theory that has certain objects stripped out, which is nice because it means even a classical person can interpret this theory and see these symbols as just symbolic calculus. But of course, Markov Jr. and Brouwer, they took this also like epistemological and ontologically serious. For them, they said, yeah, we have here this anti-classical theory, and this is actually how you should think of functions. You should not even allow for your ontology to have these objects which map unique input to unique outputs, unless in the Russian world, for example, unless there is like also a computer program which corresponds to it. Everything else, like there is no Platonic realm where other functions exists. There is no object which corresponds to a function which returns 0 if a program does not hold, and 1 if it halts, or whatever, right? So I mean, today nobody actually seems to care about taking these axioms as seriously as to adopt them for the way to think about mathematics in general, probably because it rules out too much classical mathematics. But even if you do, you can still also then use these constructive theories and model the classical world, right? You can still use because proof is in the end, proof is constructive. You're dealing with finite numbers of derivations. There's no contradiction of thinking of proof system as something computable in this sense, it does not ontologically violate these wild axioms. Okay, I've talked myself in a little bit of a an energetically speedy state. I hope it was as exciting for you as for me. I hope, in the end, I opted for a little bit free talk, and I drifted away a little bit from my script here. But I wanted to get in a few points that hopefully made sense to you. In the next video, I will discuss a choice axiom, which implies that all functions from n to the power of n to n are locally constant, which sounds wild, right? But again, there is always, I feel, is a good way to think of these semantics as just having stripped out certain classical objects, classical functions, and then it makes sense and it's kind of exciting. Okay, and with that, I will leave it. Have a good weekend.